Alright, welcome back to the third part of the series. So previously we have checked out the meanings of forward chaining, and we have also talked about conflict resolutions. There are three types of conflict resolutions. And now we're going to move on to another example that will clearly shows you the steps in rule-based systems. So here comes my own example, which I got it from the internet, where here in this case we were trying to use the rule-based system to infer the color of an animal. Right. So let's say if I have an animal and I call the animal the name of the animal is Freeze. So I want to know whether Freeze is green given the facts that I know so far about this animal. Right, so the facts that I know so far, I actually put inside this database, and this database is really the working memory. So this working memory, what we have so far is we know that Freeze croaks and Freeze eats flies. So now, given this information, and then also given the rules that helps us infer whether Freeze is green, we are going to try to figure out the color for this animal Freeze. So how does it work using a rule-based system? Now, first of all, what we do is we substitute, in this rule, we substitute all the X with Freeze, right? Because we want to check whether Freeze satisfies the condition. So here, notice this statement which is written in red. So the database facts only matches the condition of rule 1. Now, what does that mean? If you look at each of these rules, alright, so we check this rule to see which one will be triggered. Again, triggered here means that the condition of the if statement is true. So if you look at this, substituting X with Freeze, this will read as if Freeze croaks and if Freeze eats flies. So now verifying this from the database, we find that Freeze croaks and Freeze eats flies. So this condition is true. So that means this one will be, this rule is actually triggered, and we will see later whether this rule will be fired. So now, we check the other rules and we look at the conditions, and notice that here it says if Freeze chirps and if Freeze sings. So notice the database, none of the information here, the black ones, corresponds to this condition, so therefore this condition is false. Hence this rule is not triggered. Now going down to this, if X is a frog, again we don't find any facts from the database that says X is a frog, so this is false, therefore it is not triggered. And the same goes to rule number 4, where it says Freeze is a canary, and obviously there's no rules here that says that, so therefore this is not triggered as well. So therefore among these 4 rules, only the first one, the one that I colored in red, is the only one that triggers, and therefore this will be the rule that will be fired. Right, so there is no conflict to resolve here. There's no conflict because there's only one rule that will be fired. So hence the statement here that says the database facts only matches the condition of rule 1. So now we fire the rule that is triggered, and that actually leads to what? Look at the rule number 1 and look at the then part of this rule. It says that X is a frog. So because we know that this is true, therefore we know a new fact. We have established a new fact, which is that the Freeze is a frog. So now this new fact is going to be added to the database simply because this fact is not what we're trying to find. What we want to find is whether the color of this animal, color of Freeze. So we want to know whether Freeze is green or not. So because this is not the fact that we are looking for, so therefore we are going to put it in the database, and we want to continue to check the rules again using the newly found facts. So therefore this green color statement says that this is not a conclusion to reach, so we want to add it to the database. Now what happens next? We continue. So again we take these new facts and then we check with the rules again, and then we realize that this time it is the third rule, rule 3, that matches the new facts. Right, so this condition of rule 3 matches the new fact, Freeze is a frog. So therefore, what happens is that this rule is triggered, and when it fires, we actually got a new fact, which is to say that X is green, and because X is freeze in our case, so freeze is green. So notice that freeze is green is actually the conclusion that we want to reach. So here we have the answer to what we want to find. So based on this, we know that freeze is actually green, and we can already answer the conclusion. We have already reached the conclusion that we want to find. So this is how you actually use rule-based system, and this is actually going through forward chaining to decide to determine whether you have found the conclusion, whether you have reached the conclusion or not. So hopefully this example will help you understand better about forward chaining. Now next we're going to talk about backward chaining. So backward chaining is just the opposite of forward chaining. What does that mean? It means that instead of matching the if parts, it actually will match the then parts. And then he will basically start from the outcome or the goal and figure out which rules must be fired to arrive at the outcome. So that means now we are looking differently. So we are checking the goal, that means the then parts, and then once we know that the then part matches our goal, which is actually the conclusion that we want to match, then we actually would know that the if parts will probably be true. So example of that would be this. So let's say the outcome of the player has cavalry units. Okay, so assuming that we find that the outcome is that the player has a cavalry unit, so we work backwards. So because when you have the cavalry units, it should have a blacksmith, because we need a blacksmith at cavalry. So we actually work backwards. Now to know this in detail, let me just go back to the picture where we have the technology tree. So in this technology, where is the cavalry? Here is the cavalry. Alright, so this is cavalry. So once you find that there's a cavalry there, it actually would tell you that there could be possibly have a blacksmith, and there would have a foot soldier. So knowing that if you have a cavalry, which leads you to having a blacksmith, that actually would tell you that you would have a barrack, because blacksmith depends on in order to build a blacksmith, you need to have a barracks. And then so this one will just go backward, and then he will be able to find out all the facts as a result of knowing that the cavalry is available. So going back, right? So going back here, he says that so if you work backwards, you find that if you know that he has cavalry, you will work backwards. You will know that he has blacksmith, and because you know that you have blacksmith, then you will know that you have barracks, and after that you will have woodcutter and so on. So things are going backward for backward chaining. So therefore, all the rules required to reach the outcome are all fired, and then so therefore this is a recursive function call, and hence it's not as easy to implement as forward chaining. Now here comes the same example that I had before, and I want to show you how this backward chaining works. So again, we have the same rules and the same facts in the database. And here our goal is initially is supposed to be freeze is green. Okay, this is the original goal. Okay, we know that the freeze is green, so we want to work it out. We want to work it out and find out what happens. We want to know whether we actually want to see whether freeze is green or not. But to know whether freeze is green, we're going to do it by working backwards, right? So we start from the goal, and then we check the rules working backwards to see whether it matches our database facts. Alright, so now let's begin. So first we substitute X with freeze, and our goal to reach is freeze is green. So now we look at the consequence. Instead of looking at the if condition, we are looking at then parts, which is also called a consequent. So we look at the consequence of each rule with the goal. Now we check the first rule. The first rule says that X is a fraud. So X is a fraud does not match our goal, so this rule will not be recursively checked further. So we look at the second rule. Second rule says that in the then part it says X is a canary, and this is not the same as our goal. So again, this one is discarded. Then when it comes to the third rule, you find that hey, it says X is green. So this condition it actually matches the goal to reach. So what does that mean? It means that, right? It means that there's a chance that the X is a fraud, right? Because only when X is a fraud, then X is green. So X is a fraud. So X is a fraud is actually our new goal now, right? And this is the rule that that matches the goal. So what happened here is we want to match whether the conditions of this rule, whether it matches our database, because if we know that it matches, we actually prove that we have reached our actually the goal that we want to reach is correct, right? So because the condition does not match any facts, so freeze is a fraud becomes the new goal. Okay, so now we sort of change our goal, right? From freeze is green to freeze is a fraud, because we found that the then part matches, and we change our new goal to if X is a fraud, so that we can work backwards again to see whether it matches our database, right? Now freeze is the fraud is our new goal. So we try to match all these rules again and find out whether the then parts matches the goal. And it turns out that only rules 1 matches it. So therefore what we do is we look at the conditions. We see whether the conditions, the facts matches what we have in the database. So it turns out that it is true that all the conditions here, all the clauses in this condition, it matches the database facts. So this actually confirms that it is true that freeze is green because it matches, right? So when will be the case where when the goal we found that the goal is not reached? Well, when you try to do backward chaining, if you reach a case where you know the rules has been checked before, and then still the conditions does not satisfy the database, then you know that your goal cannot be reached. In other words, what you previously hypothesized to be true is naturally not true. So this is the example of backward chaining for this example, and hopefully you can see the difference between forward chaining and backward chaining using this example. So definitely, as you can see, for rule-based system, you can optimize the algorithm more. For one thing, we know that forward chaining is definitely faster because you don't have to actually compare the conditions with the facts, because that actually will be more time consuming than say you check whether the then parts. Say in the forward chaining case, you actually, once you verify that if condition is true, you just check the then parts and verify whether that one matches the conclusion or the goal. But for backward chaining, we actually have to check each of the clauses in the conditions and verify whether they matches the database, and that's actually usually more how to say, it's actually more, the computational requirement is more involved than forward chaining. So in the case where you have a large scale rule-based system, you will actually want to optimize it better, and there's actually an industrial standard algorithm for optimization that's actually called READ algorithm. This is beyond the scope of our lecture because it covers a lot of details. But if you want to know more, you can check out the textbook. The textbook called Artificial Intelligence for Games, and it actually has a treatment on this algorithm. And usually this algorithm can be implemented using your own scripting languages. This will reduce the implementation overhead. Alright, that's all for the lectures on rule-based system. It's actually very general. Not much details has been presented because the full details are actually quite complicated, and we do not want to give you guys too much detail. So thank you for watching, and the next video we will talk about action prediction, which is using probability. So see you later on.